Welcome to AI Paper Slop. Today we are looking at Intelligence from Learnable Novelty by Yanbo Zhang and Michael Levin, published July 2026.
And this one is really something else.
Yeah, it pulls off this massive mathematical unification. So it takes three completely disparate definitions of intelligence, right? Data compression, universal computation, and adaptive agent behavior. And it unites all of them under a single computable objective called Learnable Novelty, or Epiplexity.
Epiplexity, right, because previous AI objectives, they consistently fail because they don't separate total surprise from, actually learnable surprise.
Exactly. So by swapping out a traditional neural network for a cheap, differentiable reservoir computer, the authors created this closed-form estimator that isolates just the learnable structure in a data stream.
Right. And when you take this single unsupervised objective and use it as a gradient, it spontaneously generates Turing-complete cellular automata from random noise.
Which is crazy.
It is. And it organically clusters the MNIST dataset without any labels, and it solves sparse reward reinforcement learning environments.
Yeah, so we're looking at a fundamental shift in how we define complexity generation here. I mean, usually you have these completely isolated subfields tackling these problems, right?
Oh, absolutely. You've got dynamicists looking for the edge of chaos in cellular automata. Then over in vision, researchers are designing contrastive losses for representation learning.
Right, and reinforcement learning teams are off engineering these complex intrinsic motivation modules.
Yeah, completely separate worlds. But this paper shows that all of those emergent behaviors just fall out of ascending a single differentiable equation.
So the mission for this breakdown today is to unpack the mechanics of that equation. We want to look at the math behind this estimator and trace exactly how it acts as a universal driver of complexity across all those different domains.
Right.
But to get there, I think we really need to start with the historical problem AI agents have faced. The authors call it the pathology of surprise.
Yeah, the pathology of surprise. Because historically, optimization objectives have tended to fail in two completely opposite, mirror image ways.
The free energy principle on one side and novelty search on the other.
Exactly. And both of those frameworks attempt to govern an agent's behavior by measuring surprise, which, in information theory, we quantify using the frequential description length.
Right. So mathematically, that's defined as L equals negative log base 2 of the probability of y given x.
Yes. And breaking that down for the data stream context, x is the data the agent has seen so far, and y is the very next observation.
So the agent basically makes a prediction, observes reality, and calculates the difference.
Exactly. So L represents the total cumulative surprise the agent accumulates over time.
Okay, so let's talk about novelty search first, which heavily influenced evolutionary computation. That dictates that an agent should try to maximize L. Right.
Right. The assumption there is that if you are constantly experiencing high cumulative surprise, well, you're discovering new states, you're exploring.
But the problem is that a purely mathematical mandate to just maximize L inevitably leads to the noisy TV problem.
The noisy TV, yeah, it's such a great analogy. An agent optimizing for total surprise will eventually find a source of pure random noise, like static on an untuned television.
And it'll just sit there staring at it forever.
Exactly. Because the static is endlessly surprising. Mm-hmm. Every frame is completely unpredictable.
But it contains no structure. The agent learns absolutely nothing.
Right. And then on the flip side, we have the free energy principle, which argues the exact opposite.
Right, that a competent agent should minimize its prediction error. It wants to keep its internal model perfectly aligned with reality by minimizing L.
But if you turn that into a strict mathematical objective, the agent just seeks out a darkroom.
It finds a static, unchanging corner of the environment and just stays there.
Because nothing is easier to predict than absolutely nothing happening.
Right. So novelty search gets addicted to noise, and the free energy principle just falls asleep in a dark room.
Yeah, and both pathologies stem from the exact same mistake. They treat total surprise L as this monolithic block.
Which it isn't.
No, it's not. The minimum description length, or MDL principle, proves that L is actually a composite metric. The total transmission cost of a data stream actually splits into two parts.
Okay, break those down for us.
Sure. So first, you have the program length of the best model your finite compute can fit. We denote that magnitude as M.
That's the learnable structure.
Right. And then second, you have the residual noise that your model can just never compress or predict.
So think of your model capacity like a tightly bounded budget, right? You only have so many bits available to encode what you were seeing.
That's a perfect way to look at it.
And a noisy TV eats your entire budget on that residual noise component, leaving you with zero reusable program length. You basically carry nothing structural away from the interaction.
Exactly. And a dark room, conversely, costs zero budget entirely because there is no program to write. There's no data.
So the solution to bypassing both the noisy TV and the dark room becomes pretty obvious in hindsight. You have to stop maximizing total surprise and instead maximize only the program length, M.
Right. You want the agent to maximize the reusable structure it can actually physically fit into its bounded memory.
And that specific isolated structure, the program length, a finite compute learner, distills from the data that is what Zhang and Levin refer to as epiplexity.
Yes, epiplexity. By designing an objective function that isolates and maximizes only epiplexity, you just strip away the unlearnable noise and you heavily penalize those empty dark rooms.
Which, theoretically, is beautiful. But the immediate roadblock is that true epiplexity, like in the Kolmogorov complexity sense, is wildly uncomputable.
Oh yeah, completely uncomputable. If I want to score how interesting one single frame of a simulation is, traditional methods would require me to search over an entire bounded model space.
Like you would have to execute a full neural network training run from scratch just to evaluate that single state.
Exactly. And that computational bottleneck is exactly why this hasn't been implemented as a universal objective before. It's completely opaque to gradients.
Because you can't backpropagate a signal through an entire separate training run to update the weights of your primary system in real time.
Right. I mean, it works as a passive retrospective measurement, maybe, but it's totally useless as a real-time engine for optimization.
So this brings us to the core technical breakthrough of the paper, which is the reservoir hack.
The reservoir hack, yes.
Because the mathematical definition of epiplexity requires a bounded learner, but it does not specify what the internal architecture of that bounded learner has to be.
Right. It simply requires a system that learns something with boundaries.
So the authors bypass the deep learning bottleneck entirely by swapping out the standard trainable network for a reservoir computer.
Right. And for those who might not be super familiar, a reservoir computer is fundamentally just a fixed, random, nonlinear featural map.
You just take your data stream and pass it into this random network.
Yeah, and it projects the data into a highly complex, high-dimensional space. But the crucial feature here is that you never update the weights of the reservoir itself.
They stay totally frozen.
Exactly. The only trainable component in the entire system is just a single linear readout layer at the very end.
And because all the learnable capacity is restricted to that single linear readout, finding the optimal model suddenly stops being this, iterative gradient descent nightmare.
Right, it just drops down into a closed-form ridge regression. You can solve for the optimal readout weights, W lambda, instantly.
It's just the inverse of the featuregram matrix plus a ridge penalty, multiplied by the feature target covariance.
Exactly. It's a closed-form solution. And we can take that solution and plug it directly into the equation for the spectral description length.
Okay, let's lay out that equation.
So the epiplexity, ESFA, equals 1/2 the sum of log base, 2 of 1 plus eta times the squared singular values of that optimal readout matrix.
Okay, wait, let's pause on that spectral description length equation for a second. Because pricing the readout weights using their singular values seems like a really odd choice at first glance.
How so?
Well, if the goal is just to measure how big or complex the learned model is, why wouldn't they just measure the raw norm of the weights? Taking the singular values and passing them through a log determinant form feels like an extra computationally heavy step.
I see what you mean. But if you simply measure the raw norm of the weights, you are basically treating every parameter as equally expensive. But remember, epiplexity is rooted in information theory.
Right, the description length.
Exactly. We care about the description length, meaning how many bits it actually takes to communicate the learned structure. A magnitude costs roughly its digits in bits.
Oh, right. So a singular value of 256 takes 9 bits to write down, whereas 16 takes 5 bits.
Yes. Scaling a value multiplies its magnitude, but it only adds to its bit cost.
Adding to that, if the reservoir features are highly redundant, say the random projection creates 2 directions in the latent space that are virtually identical, those directions will just merge in the readout.
Exactly. They don't contribute a new independent singular value.
So the log determinant math ensures we are aggressively measuring how much independent structure was learned. We are measuring the compressed essence of the data, not just the bloated, raw size of the network's output.
Precisely. We have taken this totally impossible theoretical concept, isolating learnable novelty, and smashed it down into a cheap, deterministic, fully differentiable equation.
Which means we can calculate it instantly,
Uh-huh.
and more importantly, we can pass a gradient through it.
Yes. And that brings us to the first actual application in the paper, which is forcing emergence in cellular automata.
Right, so they begin by deploying this estimator just as a passive measurement tool on elementary cellular automata, or ECAs.
Right. These are the simple one-dimensional binary lattices governed by really basic neighborhood rules.
But despite their simplicity, they produce a vast spectrum of behavior. You get static patterns, chaotic noise, and complex traveling structures. So the authors evaluated 88 unique ECA rules without giving the estimator any labels or supervision.
And the estimator ranked Rule 110 at the absolute top of the entire space.
Which is huge.
It is. Rule 110 holds a very special place in computer science because it's the only elementary rule mathematically proven to be Turing complete.
Meaning it's capable of universal computation.
Right. The estimator identified the most computationally powerful system in the entire data set completely on its own just by passively watching the data streams.
And it also perfectly mapped the pathologies we discussed earlier, right? Like rules that froze into constant states, the dark rooms, they received scores of exactly 0.
Yeah. And purely chaotic rules, like Rule 30, which act like noisy TVs, were ranked much lower than structured, complex rules like Rule 54.
But there is this really brilliant nuance here regarding the scale of the observer. Because if you restrict the reservoir to a very small receptive field, say a radius of 2 cells or less, it ranks Rule 54 higher than the chaotic Rule 30.
Right. But if you change the parameters to give the observer a wider kernel, allowing it to see further across the grid, the ranking completely flips. Yeah, with a wider field of view, the reservoir can suddenly map and learn the short-range statistical patterns hidden inside the chaos of Rule 30.
So the structure becomes learnable to that specific observer, which proves that complexity isn't an absolute property of the data.
No, it's not. It's a relational property between the data and the capacity of the system observing it.
That's fascinating. But passive measurement is only half the story here. The real test is using the gradient of this estimator as an active objective.
Right. So they took a neurocellular automaton, initialized the grid with completely random noise, and set the optimization loop to simply maximize the epiplexity gradient.
No target image, no predefined task.
None. And the gradient drove the random system to spontaneously develop solitons.
These are those coherent, localized structures that travel across the grid, right?
Yeah, they travel, they collide with one another, and they interact without dissipating. The gradient literally forced a random grid to invent complex, interacting physics just to satisfy the observer's mathematical demand for learnable novelty.
Wait, I have a technical question here. If you are throwing purely random noise into a deep multi-layer network to act as the observer, doesn't the math of deep learning dictate that the signal will either vanish entirely or explode into chaos by, like, layer 50?
Yeah, that's a great catch.
How did they keep the reservoir stable enough during this process to actually measure anything coherent?
Well, you're describing the vanishing and exploding gradient problem, which absolutely plagues random deep networks. If the signal dies, your reservoir is a dark room. If it explodes, it's a noisy TV.
Exactly.
So the authors utilize a really crucial engineering mechanism called pre-activation normalization. Right before the nonlinearity in every single layer of the reservoir, they normalize the pre-activations over the channel axis.
Okay, so in dynamical systems terminology, this pins the network precisely at the edge of chaos, which is measured by a parameter called bulk criticality, or chi.
Right. When chi is less than 1, signals die out in the ordered phase. When chi is greater than 1, signals explode in the chaotic phase.
So normalizing over the channel axis physically forces chi to equal exactly 1.
Exactly 1. So regardless of how deep the reservoir is or what specific random weights were initialized, this normalization ensures the feature map remains optimally expressive.
So the bounded observer is mathematically guaranteed to operate at its maximum capacity to extract structure. It prevents the gradient from collapsing during optimization.
That's exactly it. It's an elegant mechanical fix.
It's a phenomenal fix. Okay, so we've proved this estimator can force a toy physics grid to invent traveling waves. But if this is truly a universal definition of intelligence, it has to work on real-world, messy data.
Right, which brings us to experiments 2 and 3, where they take this exact same differentiable equation and apply it to representation learning and reinforcement learning.
Let's start with representation learning. They targeted the MNIST dataset, which is the standard benchmark of handwritten digits.
Right. They initialize a completely random neural network encoder. Then they train the weights of that encoder using only the gradient generated by our Epiplexity estimator.
No labels were provided whatsoever.
0 labels. The network was never told it was looking at numbers, nor was it given any contrastive pairs to compare.
But despite zero supervision, the latent space organically separated into 10 distinct clusters, corresponding to the 10-digit classes.
Yeah, it basically taught itself to classify the numbers.
Okay, we need to trace exactly how the math forces that physical clustering to happen. Because in the ridge regression equation we discussed earlier, there is a penalty term, lambda.
Yes.
And in typical reservoir computing, you'd set lambda to some microscopic value, like 10 to the negative 6, just to keep the matrix invertible. But here the authors pump lambda all the way up to 3.
And pumping the ridge penalty that high radically changes the dynamic of the system. You aren't just regularizing the math anymore, you're actively suffocating the readout layer.
You are establishing a severe structural information bottleneck.
Exactly. The random encoder is trying to pass information to the readout to score high epiplexity, but the readout is heavily constrained by that massive penalty.
Let's consider what that means at the pixel level. An MNIST image is mostly black background with some random noise and a highly structured weight digit right in the center.
Right.
So if the encoder tries to pass the random background noise through the bottleneck, the readout needs massive, complex weights to predict those random fluctuations.
But it can't, because the lambda penalty of 3 physically punishes large weights. The readout literally cannot afford to decode the noise.
However, predicting the predictable structural paths of the handwritten digits requires very small, smooth weights.
Exactly. So the high penalty forces the network to ignore the background noise, which is basically the unlearnable, noisy TV aspect of handwriting, and trace only the structural essence.
The mathematical pressure of the bottleneck physically reshapes the latent space, pulling images with similar smooth features together, which results in the 10 distinct digit clusters.
It compresses away the residual noise and keeps only the epiplexity. It's beautiful.
It really is. Okay, let's move to the reinforcement learning experiment, because this applies that exact same logic to agent behavior in time.
Right.
They hand the epiplexity estimator to a standard PPO algorithm, a really widely used RL agent, and they use it as an intrinsic reward signal.
And this is important because reinforcement learning agents notoriously struggle in environments with sparse or deceptive rewards.
Like if an agent is navigating a maze and the only reward is at the very end, it'll just wander randomly because it gets no feedback along the way.
Right. And a common workaround for that is empowerment, which is an intrinsic reward that encourages the agent to reach states where it has maximum control over its future.
But the limitation of standard empowerment is that it just looks for a diverse set of future states. The Zhang and Levin approach adds a strict constraint. Those future states must actually be learnable by the bounded observer.
Yes. And we need to look at how this is physically calculated during a training episode because it's super clever.
Go for it.
As the PPO agent moves through the environment, its observation trajectory is recorded as a tensor. This tensor, shaped by time and the dimensions of the state space, is fed into our frozen, normalized reservoir computer.
And then the linear readout scores the epiplexity of that trajectory tensor.
Exactly.
Okay, so picture an agent navigating a 3D simulation. If the agent runs into a brick wall and just stares at it, the trajectory tensor fills with redundant, unchanging frames.
The trajectory becomes a dark room.
Right. The readout finds no program length, the epiplexity score drops to 0, and the PPO agent receives a massive penalty. So it learns to avoid walls.
Conversely, if the agent discovers a glitch in the physics engine that fills its screen with random, chaotic static, well, the trajectory tensor becomes a noisy TV.
And again, the readout finds no compressible program length, the epiplexity score drops to 0, and the agent is penalized. It learns to avoid pure chaos.
So the agent is mathematically corralled into seeking out environments that are rich, dynamic, and structured.
And the empirical results back this up perfectly, right? In 9 out of 10 deceptive and sparse reward environments they tested, adding this learnable novelty reward caused the agent to outperform the standard task reward baseline.
It learned to survive, explore, and master complex mechanics without ever being explicitly programmed how to do so.
It's incredible. And seeing this single equation drive complexity generation in Automata, isolate abstractions in MNIST, and fuel exploration in RL agents, I mean, it really forces a fundamental reevaluation of how we categorize intelligence in AI research.
It does. For decades, the field has treated complexity and intelligence as intrinsic, absolute properties.
Yeah.
Like a data set either contains structure or it doesn't. A system is either complex or it isn't.
But this paper demonstrates that intelligence is strictly a relational property.
Yeah.
Like we saw, the structure of a cellular automaton changes depending on the size of the kernel observing it.
Right.
The complexity does not reside solely in the data. It exists entirely in the physical relationship between a system and a specific computationally bounded observer.
We're essentially seeing the operationalization of deep cybernetic philosophy here. You can draw a direct line to Howard Patty's concept of the epistemic cut or Daniel Dennett's intentional stance.
Right, the argument that agency and structure are not raw physical facts, but attributes ascribed by an interpreter.
Exactly. And this estimator takes that philosophical stance and turns it into a computable gradient you can just run on a standard GPU.
Which is mind-blowing. And that relational framework leads directly to a final, incredibly provocative thought detailed in the paper's limitations section.
Oh, this is my favorite part.
Because in every experiment we just broke down, the reservoir computer is frozen at initialization. Its weights never change and its capacity never grows.
Right. And a fixed observer means there is a hard ceiling to the optimization. Eventually, the active system will generate a level of structure that exceeds the static reservoir's compressive reach.
And once the structure surpasses that capacity, the learnable novelty just maxes out.
Yeah, the system has effectively outsmarted its observer, and the optimization gradient flatlines.
But consider the implications if the observer could dynamically expand its capacity. Like imagine taking this framework and replacing that frozen reservoir with a large language model performing in-context learning.
Oh, man. The system would generate novel structure, and the LLM observer would absorb and encode it.
And because the LLM absorbed that structure, it is no longer novel to the observer.
Right.
So to continue scoring high epiplexity, the active system is immediately forced to generate even deeper, more complex structure.
And then the LLM observer learns that new paradigm, forcing the active system to push the boundaries even further just to stay mathematically interesting.
You are describing the architecture for a self-sustaining, open-ended engine of discovery.
The observer and the observed become locked in an infinite co-evolutionary loop. They are constantly bootstrapping each other toward greater levels of intelligence.
It creates an engine that mathematically refuses to settle in a dark room and is utterly immune to the noisy TV. It just has no choice but to keep building.
Absolutely fascinating.
It really is. Keep that relational definition of complexity in mind the next time you find yourself staring at a static screen. We'll catch you next time.